Students, in this video, let us discuss about transient response of RL circuit, decay of current case. In the previous video, we have discussed rise of current case. In continuation with that, we will discuss decay of current case in this video. So I have taken a circuit like this. You can see that resistor R and inductor L are getting connected in series. There is a supply V and there is a switch here. So now I am going to assume that the switch is in the position 1 for longer time. So when the switch is in the position 1 for longer time, there is a closed loop formed by V, R and L. When there is a closed loop formed, the current starts to flow and the current will exponentially increase and it will reach a steady state value. So what is the value of the steady state current? During steady state, this inductor will behave as a short circuit. So the current is drawn from the supply only will be V by R. Okay, so when the switch is in the position 1 for a longer time, the circuit would have reached a steady state. The steady state current that is flowing in this loop will be I is equal to V by R. So now I am going to bring this switch to position 2 at time t is equal to 0. So initially I am charging this inductor and now I am going to bring this switch to the position 2. So this is a switching activity that I am doing. At time t is equal to 0, I am bringing the switch to the position 2. When I lock this switch to the position 2, then there is a closed loop formed. Let me apply Kirchhoff's voltage law and write the loop equation for this loop. Okay. So let me take the loop current to be I of t. So applying KVL, R into I of t plus L into di of t by dt. So you can note that there is no supply in this loop now. Okay. If there is a supply here connected, then you can write that in the right hand side. But there is no supply connected here, so it is equal to 0. So let me apply Laplace transformation to this equation. So it will become R into capital I of S plus L into S into I of S minus I of 0 is equal to 0. This I of 0 is nothing but the initial current that was flowing through the inductor at time t is equal to 0. See, when I lock the switch to the position 2, before that activity, there was a steady state current capital I flowing through this particular inductor. So this I of 0 is nothing but the initial current through the inductor, which is nothing but V by R. So let me substitute that here. R into I of S plus Ls into I of S minus L into I of 0 is V by R, because at time t is equal to 0, when I locked the switch to the position 2, there was a current flowing through the inductor, which is nothing but the initial energy. We call it as initial energy stored in this inductor, that is I of 0 is equal to V by R. So I have substituted that, since I of 0 is equal to V by R. Let me rearrange this particular expression to get I of S. I of S is equal to L into I divided by Ls plus R. So you get I of S is equal to I divided by S plus R by L. So now it is easy for the students to take inverse Laplace transformation because there is only one denominator term. So after applying inverse Laplace transformation, you will get I of t. I of t is nothing but I of t is equal to, I is a constant, capital I, 1 by S plus some constant. When you take inverse Laplace transformation, it becomes e power minus that constant into t. So this is your expression for I of t. So the current, this I of t is nothing but the initial current, the steady state current I that was flowing through this inductor, that is getting decayed. Slowly it is getting decayed, e power minus r by L into t. This will get decayed and it will reach 0 as time tends to infinity. So that's why it is called as decay of current case. So let us also find the voltage drop across this resistor, that is VR of t and VL of t. Okay, VL of t. Summation of these two potentials is equal to 0. So VR of t is nothing but VR of t is nothing but I of t into R. So this is I of t, I into R e power minus R by L into t. I into R is nothing but V according to this equation. So VR of t is equal to V into e power minus R by L into t. This is expression number 2. And since VR of t plus VL of t is equal to 0, VL of t is equal to minus VR of t. So VL of t is equal to minus V into e power minus R by L into t. So this is equation number 3. So here is the graphical representation for the equation number 1, 2 and 3, and you can see that the current, that is here, the current in this loop, okay, it decays to 0. So the initial current through the inductor and the resistor was the steady state current, that is capital I, and when the switch got locked to this position 2, that current I slowly decayed to 0. So you can see that I of t decays to 0 when time t tends to infinity. So this is the pictorial representation of this equation number 1, and here correspondingly you can see that this is plus V and this is minus V. These are the graphs for VR of t and VL of t. So in the next videos, let us do some problems so that students will have better understanding on the transient response of circuits.